Welcome to the Calculus BC video for skill number 235. I can apply the mean value theorem. And pictured below is a graphic for the English or flat saddle. And the trivia question is, the pommel is located at the front or the back of the saddle. And if we want to go one step higher, what is a pommel in terms of architecture words? Alright, so the mean value theorem is a theorem that we use in calculus that gets used in a variety of ways, but what we should understand is that there is two conditions which must be met in order for us to apply the mean value theorem. The first condition is that the function is continuous on a to b. So if I have an a and I have a b, my function has to be continuous from a to b. The next thing is the function has to be differentiable on the open interval a to b. So here we have a differentiable function. An example of something that's not differentiable would be like it comes to a cusp, like that. If condition 1 and 2 are met, then there is a number c in the interval a to b such that f prime of c equals f of b minus f of a over b minus a. Or more simply stated, the slope of the secant line is equal to the slope of some tangent line within AB. So here we have the secant line, there's some tangent line within the interval of A to B, located at a value of C. So I wrote that kind of in layman's terms down here. Simply stated, there exists a tangent line in the interval AB with a slope equal to the slope of the secant line from A to B. And I kind of drew a very simple graph of it that says the slope of the secant line is equal to the derivative at C. This is a very simplistic, probably I would argue mathematically incomplete statement, but it's getting the idea across from above. So let's take a look at some examples. Before we get to example 1, Rolle's theorem is just an extension of the mean value theorem. It's the same as the mean value theorem with our first two conditions, but then we add a third condition, which is that the f of a is equal to the f of b. So instead of having a and b at different heights, we find a and b are at the exact same height. So the slope of our secant line is actually 0, so there's some point within the curve that also has a slope of 0. In example 1, we're verifying that the given function satisfies the conditions of Rolle's theorem, and then we're going to find all numbers that satisfy the conclusion of Rolle's theorem. So what we have here is a function, and the function exists on the interval 1 to 3. And so first we check, is condition 1 met? And the condition 1 says continuous on the closed interval. Well, this particular function is continuous everywhere, and we know that's true for all polynomials. So if it's continuous on all real numbers, then it's definitely continuous on the closed interval 1 to 3. The next condition is that it's differentiable on the open interval. Well, polynomials are differentiable everywhere, so we can say that it is differentiable on the open interval 1, 3. And then finally, the third condition of Rolle's theorem is that f of a equals f of b. So if we calculate out f of a, we find that to be equal to -4, and if we calculate out f of b, we find that also to be -4. And since those two agree, then all three conditions are met, and we can seek out the c which satisfies the conclusion. So if we take the derivative of the function, we find that the derivative of the function f prime of x is -12 plus 6x. And when we're trying to satisfy Rolle's theorem, basically we're saying f prime of c equals 0. So we can plug c into the equation, set it equal to 0, and find that c equals 2. which means on this graph at x equals 2, we have a horizontal tangent line. So maybe the graph does something like this. So we now know that the graph has a horizontal spot at x equals 2. Maybe this was 1 and this was 3. Alright, that's the first example. Let's take a look at some calculus in motion. Alright, here we are again using calculus in motion, and this time we're using the mean value theorem for derivatives. And the mean value theorem says that if a function is continuous on the closed interval a, b, then we have a continuous function on closed interval a, b, and it's differentiable on the open interval a, b, and we have a function which is differentiable on the open interval a, b, then there is some c between a and b, so this sliding value of x. Somewhere along this sliding value of x, we are going to hit a point where the slope of the tangent line is equal to the slope of the secant line which connects a and b. So obviously if I stopped right here, that point is not parallel to a secant line from a to b. And so the goal is to find a C where it is parallel. So perhaps I can slide my C, or in this case x value, all the way along until about right there. I think that point is probably parallel to the secant line. As you can see, I'm maybe a little bit off. Maybe I'll continue sliding C right there. That looks really close, or better. Nope, I don't know. So at least there is a point in there. I can actually get this to highlight it so that as I'm moving along, when I hit that point where we're parallel, it highlights the C value. And as you can see in this particular graph, there's two spots at which a tangent line would be parallel to the secant line, which connects the two. We can take this a little bit further and connect it to the Rolle's theorem, which is very close to the mean value theorem. The only difference is it has a third condition. That third condition is that f of a and f of b have to be at the same height. So the way we can prove this is, first what we do is we think of the secant line, and then we can subtract one function from the other, and if we move those values up there, we are going to create a second equation. And as you can see, the second equation, we have an f of a and an f of b at the same height. So that means that somewhere along the way we hit a C value where the tangent line is horizontal. So the important thing to remember is that for Rolle's theorem, we just have the third condition that f of a and f of b have the same height. Let's take a look back at the mean value theorem real quick. All right, so here I've created a second equation, and what we're doing is we're trying to find the C value for which the tangent line is going to have the same slope as the secant line. And if I click on Show C, then it should highlight when we get there. And we move along, and we notice no C gets highlighted. And the question is, why is that the case? And the answer, very simply, is because the function is not differentiable at 3. So it fails to meet the conditions of the mean value theorem. So we're not going to necessarily be able to find a C that allows us to have a tangent line with the same slope as the secant line. Let's try and adjust this graph and see if we can fix that problem. Okay, so I have not changed the original equation at all. The equation is still exactly the same. We have the same function. However, our interval now does not contain the non-differentiable point. So we should be able to find a point on the curve where the tangent line has the same slope as the secant line. So let's turn on the slope, show the secant line, and show C. And there we go. There's the value of C that contains the same slope. So for this skill, we should be able to recognize when the MVT conditions hold, or even when Rolle's theorem conditions hold. And then if they hold true, then we need to be able to find the value of C which satisfies it. And the examples in the notes will show us how to do that. So after watching that video, now we can kind of answer example 2. Draw examples of functions that fail each condition of Rolle's theorem. So in this case, condition 1, I've got all conditions met except it is not continuous. We have a break, so we cannot apply Rolle's theorem. In condition 2, I have a function that's continuous, but it's not differentiable at a point, so that condition is not met, so we cannot apply Rolle's theorem, or even the mean value theorem for these two things. And then the third condition, my f of a does not equal my f of b, and so while I'm able to apply the mean value theorem, I cannot apply Rolle's theorem. So the final example says, determine if the given function satisfies the conditions of the mean value theorem. If not, state why not. If so, find all C values that satisfy the theorem. So this is a lot like example 1. And in the first one, we're given a function and an interval of 0 to 6. And we cannot apply the mean value theorem because the function is discontinuous at 1. Remember, there's a vertical asymptote at x equals 1. In the next case, we have a polynomial, and polynomials are always very nice to us. This polynomial is continuous everywhere, it's differentiable everywhere, and f of 2, well, we don't have to test for Rolle's theorem, so it's continuous and differentiable everywhere. So we can satisfy the conditions of the mean value theorem, so we should be able to find a C. So we take the derivative, and we take the slope of the secant, and we find that the derivative is equal to the slope of the secant at a C value of 3. Alright, so we should be able to apply the mean value theorem now, which basically says that if you have some sort of curve from point A to B, and if it's differentiable from A to B and continuous from A to B, then the slope of the secant line matches the slope of a tangent line at some point within A to B. To answer the trivia question, the pommel is located at the front of the saddle. So here we have somebody wearing boots and they're coming down. My drawing is no good today. Anyways, they sit there. And the secondary trivia question is, a pommel in architecture is a spherical ornament or finial. For example, in this cap to what I imagine is a gazebo, what we have is a spherical piece called the finial or the pommel.